Welcome back to Unit 5 on vectors. We are on Lesson 3, Applications of Geometric Vectors. Ships and aircrafts frequently need to steer around dangerous weather. The pilot must consider the direction and speed of the wind when making flight plans, and heavy objects are often lifted by more than one chain hanging from a horizontal beam. So velocity directions are often expressed in terms of a compass bearing. Vector situations such as these can be modeled using triangles. Knowing the net effect of a number of forces determines the motion of an object. The single force, the resultant, has the same effect as all the forces acting together. We will use vector addition, Pythagorean theorem, and trigonometry in order to solve problems involving triangles. First off, two vectors are perpendicular to each other and add together to give a vector v are called rectangular vector components of v. So vectors can be resolved into horizontal and vertical components, and often it is useful, particularly in cases of physics type problems, to just analyze either the horizontal component or just the vertical component. In other cases, you'll see problems where you're given either the vertical, or you're both the vertical and the horizontal, and are asked to find the resultant. Consider example number 1. A box weighing 140 newtons is resting on a ramp that is inclined at an angle of 20 degrees. Resolve the weight into rectangular vector components that keep the box at rest. Okay, so let's consider this question. So, geometric vector problems. First thing you should always do, unless they give you a diagram, is to draw a diagram. Okay, so we have an incline. Here's our incline. Okay, here we go. And this is going to be 90 degrees. Okay, this type of question is more of a physics type question, but they're really, really useful in solving vector problems. And you'll find in most cases in this unit that most of the problems are actually going to be based around science or physics. And those of you who are going into business might not be able to relate to, but bear with me and we'll get through it. Okay, so here we have it. The angle of incline we said was 20 degrees. Okay, and gravity usually acts this way. Okay, so 20 newtons is the weight. Okay, is the weight of the box. So basically, weight of something is its mass times gravity. So we don't actually have to include gravity. We can just say that the weight is 140 newtons. And you can do that when we're actually given newtons. We know that it's the weight of the object. Okay, so this surface, this box is sitting on this surface. Now, when anything is resting on a surface, the box is pushing against the surface as the surface is also pushing against the box. We call this force the normal force. And it's always perpendicular to the surface. Okay, and always acting in the opposite direction of the box, of the force of the box or whatever object it may be. Okay, what else do we have here? We also have friction. We have to have friction acting in this direction. Okay. I'm going to label that N. Okay, so there's all of our vectors that's acting on our box. Okay, so I'm going to redraw all these vectors in a different orientation so that looks a little bit more clear. So we have the normal force, we have the force of friction, and then of course we have 140 newtons. And all these forces are working together in order to keep the box stationary. Okay, that's 20 degrees. So basically what we're going to be doing is we're going to shift our XY coordinates this way, okay, so that the X runs along the horizontal of the incline. Okay, so in this case what we're saying is that this is vertical and this is horizontal. So we're going to take our weight and we're going to split this up because it's the only one that's on an angle if we look at our new coordinates. Okay, So just doing this, I'm just going to do this just so that you can see X, and this is Y, okay? So we're going to take 140 and we're going to break it up into its horizontal and vertical components. And the reason we want to do that is because both N and F are adding together. The vectors you see tip to tail are adding together to give you 140 newtons. So if we break them up, then we can see what the magnitude of N is and what the magnitude of F is. So remember, SOHCAHTOA, SOHCAHTOA, okay? And we can simply say, so this is 20 degrees here. Okay, so if I wanted to find N, okay, with respect to 20, N is then the adjacent and hypotenuse, so cos, right? Cos of 20 degrees is equal to the magnitude of N over 140 newtons. And now I just rearrange to isolate for N, I have 140 cos of 20, okay, which would then give me around 131.6 newtons. Okay, so that's my normal force. Okay, so if I was to do the same thing now with F, so F is opposite, 140 is hypotenuse. Let me just draw my 90 degrees there, just to make that more clear. So sine of 20 degrees is equal to opposite over 140. Okay, so the force of friction, the magnitude of the force of friction is 140 times the sine of 20 degrees, which would then give us, if we were to put that in the calculator, 47.9 newtons. And there you are. So moving on, an equilibrium vector is one that balances another vector in a combination of vectors, or a combination of vectors. It is equal in magnitude but opposite in direction to the resultant vector. If the equilibriant is added to a given system of vectors, the sum of all the vectors is 0. Okay, so it keeps it in balance. In order to better understand this concept, let's go through an example. Consider this example. So a traffic light at an intersection is hanging from two wires of equal length, making angles of 10 degrees below the horizontal. The traffic light weighs 2,500 newtons. What are the tensions in the wire? So although we were given a diagram for this question, let's go ahead and draw a vector diagram of the two tensions. Let's see now. So what we have here is the light. We have the light, we're going to say has a weight. We were told it has a weight of 2,500 newtons, okay? And so tension always acts away from your object. Okay, so think of a rope. Okay, so if you're pulling on this rope, the rope is also pulling back, and that's exactly what tension is. It's the force it's pulling back. Okay, so there are the two ropes there. Okay, so T, we'll just label them T2, T1. Okay, so here's our horizontal. Okay, and we have 10 degrees here and 10 degrees here. Okay, so we're going to say let T1 and T2 represent the tensions. And remember that they're going to be equal in magnitude, okay, because they're the same angle. They have to be equal in magnitude or this object would be moving, or the traffic light would be moving. So in this particular example, this weight pulling down is actually our equilibriant. Vector, okay, that keeps everything in balance. Okay, so let's move on to actually finding the tensions in each of the wires. Okay, so let's take our tensions and draw them tip to tail. Okay, this is a little tricky, but you get used to being able to visualize, and it's all about practice. So let's just take our T2 here. Okay, so I've done an all right job. T2. Okay, and then we have T1 right here. And what's going to happen now, we can just draw a resultant from T1 and T2. So it should be pretty straight up and down, but I think my diagram's a little bit off there, and you're going to see that you're going to have that problem. But okay, so here we can say this was 10 degrees, okay, if that was T2. Using the Z pattern, this here is also 10 degrees, okay? And if you're picturing this one, that's also 10 degrees there, okay? So that vector is T1, so that angle there corresponds to this angle here. Okay, so T1, okay? So this is 2,500 newtons. Okay, so it has to be pulling upwards. There has to be a vector that pulls up. Remember that the resultant force is always opposite in direction and the same magnitude as the equilibrium vector. Okay. Okay, so let's further examine our diagram. Now, my diagram's not that great. Maybe if I tilted it like that, you'd see that what we have is two tensions of the same length, okay? If they have the same length, that means that these two angles have to be the same. Okay, so what we have is an isosceles triangle. So we know that in a triangle, any triangle, all the angles, the sum of the angles is 180. So we could say 180 degrees minus 20 degrees, we're left with 160, okay? So altogether they have to equal 180. We know this is 20, so that means between these two is 160. Dividing that by 2, we've got 80 degrees. So each of those angles are going to be 80 degrees. So now we can simply just solve this triangle as if it's a non-right angle triangle. And remember, when we do that, we have to use either the cosine or sine law. I prefer using the sine law. I find it easier. So let's go ahead and do that. Let's take T1. Let's just take T1, okay? I always put, for the sine law, I always put what I'm looking for on top. So if I'm looking for a length, I put it on top. If I'm looking for an angle, I put sine of the angle on top, okay? Then I'll go sine, whatever is opposite to, which is 80 degrees. Okay, we'd already established that those are 80 degrees, is equal to, and this magnitude is 2,500 newtons over 20. So sine of 20 degrees. Okay, so now we can solve for T1. And let's go ahead and punch that in our calculators. Okay, so we should get 7,198 newtons. Okay, and that is, for this, at 110 degrees below the horizontal. And T2 will be the same. T1 is equal to T2. Okay? Previous lesson, we looked at compass bearing questions. We're going to take that a step further and examine questions that I call airplane questions or heading questions. A few concepts to cover first. A heading is the direction in which a vessel is steering to overcome other forces. For instance, if you are on the opposite side of your campsite and you are separated by a river, the river has a current and you needed to swim back, you wouldn't simply just head straight towards your campsite. You would need to swim on an angle, or else you'd be swept downstream. Ground velocity is the velocity of an object relative to the ground. It's the resultant or bearing velocity when the heading velocity or air velocity is affected by wind or current. Let's look at our final example. An airplane is flying at an airspeed of 500 kilometers per hour on a heading of 040 degrees. A 150 kilometer wind is blowing from a bearing of 120 degrees. Determine the ground velocity of the airplane and the direction of flight. Okay, so the first thing that we should do, of course, is draw a diagram. So I'm going to draw my compass bearing, okay? North, south, west, east. Okay. So our airplane is flying at an airspeed of 500 kilometers per hour at a heading of 040. Okay, so that's true bearing, so we're going to take that bearing from north. Okay, and let's see, we'll still use this marker, 40, so that's roughly 40 degrees, I'm going to say, right there, and that is 500 kilometers per hour, okay, and that's 40 degrees. And then we're also told that a 150 kilometer wind is blowing from a bearing of 120. So that's the tricky part, is that it says from. So 120, so that's 180. So we're going to say this is roughly 120. So before I draw my arrow, okay, I just want you to note, okay, let's see, the wording, 120 degrees from. Okay, so 20 degrees. Okay, so it's from. So does it mean that it's actually going this way? No, it's coming from. So the opposite, the arrow should be pointing in the opposite direction. There we go. Like that, because it's from. Okay, and that we were told that is 150 kilometers per hour. Okay, we want to determine the ground velocity of the airplane and the direction of flight. So that will be the resultant. Okay, so I'm just going to move the one vector. Now, I just want to know, because I wanted you to see this vector clearly, but I've really exaggerated it. It's really big. It's actually almost the same size as the 500 kilometers per hour. So we're just going to shorten it up a little bit so it is a little bit more accurate. There we go. So it's 150. And I've just used the red, so I'm going to have to use a different color. Let's see. Now, we can do this one of two ways. We can draw a parallelogram, okay, or we can completely move the vectors around. It's up to you. I can actually show you both. So here, down here, what we can do is redraw it as being, my drawing is atrocious today, because I can't seem to even get the same angles there, but kilometers per hour, and then 150 kilometers per hour, okay? So we can say that this is then the resultant, and this angle right here, okay, so that's 120, and we subtract 40, that angle here is then 80 degrees. 80 degrees, and we will want this angle, okay? So we're going to want this angle here, because that'll tell us where our resultant is. So you can do it this way, so you have tip to tail. Another way we can do this is to draw a parallelogram. Okay, let's use a fine pen for this. So what I can do here is draw, okay, and then, so you might be able to see that. You can see that I have a dotted line, okay, and then straight across. You can even use, I would use rulers just to make sure that you've got everything. There we go. And that's our resultant, which is the diagonal across from the parallelogram. What you then do is, you can find this angle, by saying that if this is 120, you would find this angle here, and that will give you this angle, and minus it from 90 to give you this angle. Okay, so once we have that angle, we know this is 40, we add 40 to x, and that gives us this angle, which will be equal to this angle, okay? And then we can simply subtract from 180 to get these two angles and divide by 2. In this case, it's probably easier to do this right now, but there will be cases where you should do this. It's easier to visualize if you were to do it this method. In this case, I'm just going to go ahead and follow through with this one, since we've already got it drawn. Okay, so in order to find our resultant, let's see, what do we have? We have two sides, we have an angle, and across from it is our unknown cosine law. You're going to get to like your cosine law in this unit, or dislike it. 150 squared plus 500 squared minus 2 times 150 times 500 cosine of 80 degrees. Okay, and we would simply plug that into our calculator. And that works out to be a really big number. Let's square root that. The magnitude of r is then equal to 496.4. And we're dealing in kilometers per hour. Okay, and now we need to find our bearing, because this only gives us the magnitude. So we can use the sine law. So again, want to find an angle, so we put it up top. Okay, so this angle, the opposite to that is 500. And then we can say the sine of 80. Okay, and we know what r is. We'll hope that it's right. Theta then is equal to 82.7 degrees. Okay, so what exactly, let's interpret the results. What exactly does 82.7 degrees mean? Okay, we said, okay, if we were to redraw this, remember that I originally drew the wind direction. That's the word I'm looking for, the wind direction there. So we're just going to go ahead and do that. Then we said, well, we can draw. Basically, I'm just taking the triangle and redrawing it here, okay? And putting the resultant at the origin. That'll help us to put it in either true bearing or quadrant bearing, okay? In this case, true bearing will probably be the easiest here. So if this is 2.7 degrees, okay? Now we need to either find this angle, the small angle, or this angle. Either one will give us the other. Okay, so that's 82.7. I'm not sure if you can see that, but that's 82.7. This is R. This is 500. This is north. And 150. Okay, so what I would do is I know that from here to here was 120, right? From here right to there was 120. The entire length here is 180. This has to be 60. Okay. Opposite angle theorem. This means that this is 60 right there. Okay, that's 60. So I'm going to put a little X there. I know these diagrams are so small. And even if when I do this on a whiteboard, you are putting so much information on one diagram that it still looks jumbled, even when you blow it up, just because you're drawing all over the place. Do your best. Now that little angle there then, okay, we're just going to call that alpha for now, is 82.7 minus 60. Okay, and that's the trick here, is to put it in the origin there, your resultant, so that you can actually just come up with that angle, and then you have true bearing. That works out to be 22.3. Okay, so alpha. So there we go. So what we have now is therefore, let's see what we're actually asked. The plane's heading is 496.4 kilometers per hour, 23, we can round it, 23 degrees. Okay, I'm going to rewrite that. 23 degrees, 0 to 3 degrees, because we are in true bearing. Okay, if you want, you can even represent that as quadrant bearing. Usually what I do is whatever the question gives me. So if I read it and it gives me true bearing, like all of our detail was given to us in true bearing, then you want to represent your answer as well in true bearing. If it's in quadrant bearing, then you want to write your answer in quadrant bearing. Anyway, I hope this was useful today, and that concludes our lesson, and we will see you next time.